Hello everyone, I'm Chengyin Xu, a master's student from Tsinghua University Shenzhen International Graduate School. The paper I'm going to present today is titled Hypersquare Loss Beyond Hypersphere Metric Space for Multi-Label Image Retrieval. Firstly, I will introduce the research background of my work. The past decades have witnessed the arrival of the era of big data. Floods of images are uploaded to social platforms and search engines day and night, which calls for more efficient and accurate image retrieval in multimedia applications. As a matter of fact, real-world images typically contain more than one attribute. Hence, the multi-label retrieval task serves as the crucial and more challenging branch in large-scale image retrieval. One of the main challenges of multi-label image retrieval is that more objects in one image causes more complex image features. Besides, compared with single-label data, the correlation between different sets of labels needs to be considered in multi-label scenarios. The above two problems lead to higher requirements on feature embedding and metric space construction. Worse still, common image retrieval methods have limited performance in multi-label scenarios. Therefore, it is very important and challenging to explore an efficient multi-label image retrieval method. Pair-based methods are most commonly used in image retrieval tasks, which fully activate the data correlations. However, such approaches suffer high computational consumption and converge difficulty, especially are more serious and inevitable in multi-label scenarios. To address the challenging issues in pair-based methods, proxy-based methods are proposed to improve model robustness with efficient training complexity in single-label scenarios. However, they are also disqualified in multi-label tasks for some reason. Now, we are going to analyze and demonstrate the limitations of proxy-based methods from two perspectives: quantity and quality of the metric space formed by proxy-based methods. Consider the quantity term first. In multi-label retrieval, the inclusive and exclusive relations, which means the ability of metric space to distinguish its relevant and irrelevant categories, is exponential with respect to category number C. However, the isotropic hypersphere metric space formed by proxy loss has an inherent side effect in such scenarios. When the number of labels of one sample is larger than 2, the label correlations cannot get fully expressed in the hypersphere space. Specifically, we have the following theorem to illustrate the upper bound of the distinguishable hypersphere number, omega kc, or called the maximum inclusive and exclusive relations in multi-label scenarios, which reveals the primary reasons that proxy-based methods are unsatisfactory in multi-label scenarios. Simply embedding the samples distributed among a proxy-centered hypersphere cannot comprehensively introduce the combination among various categories, and the proxy-to-data supervisions ignore data-to-data attribute conflicts. As a result, some crucial label correlations may not be well expressed. Secondly, think about the perspective of quality. We illustrate this limitation with a simple example. Image V1 associated with P1, P2, dog and cat, will be embedded into the middle of P1 and P2, according to the gradient of the loss function, while image V2 with P3 and P4, cow and sheep, will be embedded into the middle of P3 and P4. However, the missing data-to-data correlations ignore the attribute conflicts between the irrelevant V1 and V2. Although proxy loss explicitly alienates V1 and P3, P4, V1 is not guaranteed away from the middle of P3 and P4, which is exactly the embedding position of V2. Hence, the dissimilar samples V1 and V2 are entangled in the same metric space. Given a query VQ with attributes P1, P2, V1 may get retrieved first, second by the closest sample V2, but ignores some relevant samples V3 with the same attribute P1, or V4 with P1 and P4. The misclassified conflicts among multi-label datasets become more prominent. The above observations motivate us to consider data-to-data relations that contribute to a powerful metric space to represent the correlations among various attributes. To avoid constructing the metric space into an isotropic hypersphere without loss of training efficiency, we creatively propose hybrid proxy pair loss for metric learning to extend the proxy loss into challenging multi-label scenarios, and compensate for the local optimum and overfitting risks for pair loss in exploring data-to-data relations. The first term of Hypersquare loss is designed as multi-label proxy loss, which only optimizes the distance between proxies and samples. Secondly, we focus on the exploring data-to-data correlations to explicitly enforce irrelevant samples get alienated. Compared to the entire m times m computation, the proposed negative loss only considers limited pairs to mine data-to-data correlations that alienates irrelevant samples effectively without loss of efficiency. Finally, the overall HyP square loss is a weighted assumption of the above two loss terms to obtain the total loss. We present the visualized TSNE comparisons between baseline proxy loss and the proposed HyP square loss. Scatters of the same color indicate the same categories. Note that the blue color presents bus, cornflower blue color represents car, sea green color presents person, dark magenta color presents train, respectively. The circled regions indicate same samples containing the above two categories simultaneously. For proxy loss, the samples containing multiple categories are distributed nearby the center position of the corresponding single label clusters, respectively. However, due to the close interdistance between the two circle samples, the confusion between these irrelevant samples becomes predominant and thus will damage the retrieval performance. As a comparison, HyP square loss explicitly enlarges the interdistance between irrelevant pairs, which tackles the conflicts effectively. Specifically, the confusing irrelevant pairs in Figure A are disentangled in proposed HyP square loss as Figure B, which demonstrate the effectiveness of the proposed method. We exhibit part of the results of the proposed HyP square loss on multi-label benchmark datasets. The top 10 images are returned according to the Hamming distance between the query image and the database. The number below each retrieved image indicates the matched categories, and the green box indicates 100% matched categories. The proposed HyP square loss exhibits satisfactory retrieval accuracy with few contradictions and misclassified results. Here we provide a table which illustrates the training complexity of HyP square loss versus previous state-of-the-art. Note that the proxy-based methods are unqualified for multi-label metric learning, while pair-based methods require OM square or even OM cube time complexity. As a comparison, HyP square loss causes more efficient training complexity since the irrelevant pairs are the minority to the whole dataset. We theoretically analyze the primary reasons that proxy-based methods are disqualified for multi-label retrieval and propose the novel HyP square loss, which introduces a crucial constraint term of irrelevant samples while preserving the efficient training complexity of proxy loss, which compensates for the limitation of the hypersphere metric space. Thanks for listening.